Morning, my name is Eric Butterfield and I'm part of Design Team 8. We are working to develop a graphical user interface for RFID MOVE sensor platforms. Our team name for short is GUI MOVE, stands for Graphical User Interface, and then MOVE being the name of our sensor. So what we're going to talk about today, we're going to start with a bit of a team introduction, describe the various technical and non-technical roles of our team members. After that, we're going to go into a little bit of project description, talk about the goals we hope to accomplish for this semester. Dan will then take over and talk about the back end of our project and the hardware and software that we plan to use for that. Taboola will introduce the front end, which is mainly our user interface that the operator will see and use. Then Minglan Lee will talk about our 3D design aspects of this project. And lastly, Sam will wrap up the conclusion, look at team management and cost. Our team. We are sponsored by the National Science Foundation and MSU Technologies. Our on-campus representative for our sponsor is Dr. Shantanu Chakrabarti, and our facilitator is Dr. Jian Ren. Our team members include Taboola Mbalakanga, who is our team manager and our GUI engineer. Myself, I'm the document prep and the hardware engineer. Samuel Richer is our presentation prep, and he is a software engineer. Minglan Lee will be our 3D design engineer and our lab coordinator. And lastly, Dan is our webmaster and another software engineer. A little bit of background about our project. A current main concern for our national government is the overwhelming cost of infrastructure health monitoring. It's estimated by the American Society of Civil Engineers that through 2014, over $2.2 trillion needs to be spent on this. A big reason for this high cost is the current methods used to monitor our infrastructure. Currently, a contractor has to go in person to a structure and visually test and inspect it. The data they collect, they then use to assign repair priorities to things like roads, buildings, bridges. As you can imagine, this is both costly and time-consuming, and has led to a need to be able to do this autonomously. The way we plan to do this is we plan to use RFID sensors embedded in concrete, attached to airplane parts, etc. Doing this allows us to track any physical changes in whatever we have it attached to, or count the amount of usage and a host of other data points. For example, airplane parts are often spec'd at either number of flights that it can sustain or flight hours. Currently, this has to be recorded and tabulated by hand. Using an RFID sensor, all you would have to do is scan the part on the airplane after a flight, and it would tell you how much longer it could go until it needed to be repaired or replaced. Another example would be these RFID sensors thrown into the concrete used in our nation's highway system. If this were the case, readers would be attached to semi-trucks that traveled over the roads often. And every time they traveled over these different sensors, they would collect data points on the road, and you'd be able to monitor the health of the road very easily. So overall, our project involves MOVE sensor platforms that are read by two 90-degree oppositely polarized antennas. These antennas then send the data to a reader that encodes it and sends it to a computer. At the computer stage is where our project is really kicking in, trying to develop a user interface that is both easy to use and aesthetic to an operator. So our three main goals for this project is to, number one, we want to be able to retrieve the distance and orientation of our sensors. Let us know if any physical changes have happened. Number two, we want to develop a user interface that displays this information to an operator. And our third goal is a secondary goal that we really hope to accomplish this semester, and that's to enable it to be cross-platform compatible between open and closed source systems. And now Dan's going to take over and talk about the back end of our project a little bit.
Okay, thank you, Eric. Hi, I'm Dan Perez. I'm going to be talking about the back-end portion of our system. The responsibility of the back end of our system is to collect data from a remote sensor, to use that data to calculate the distance and orientation of that sensor, and then to send that data on to a graphical user interface. The major components of the back end of the system are the MooWisp remote sensor, RFID antennas and reader, and software that will be running on a PC or a laptop. So the sensor that we're using is called the MooWisp. WISP stands for Wireless Identification Sensing Platform. The WISP has no internal power source. It's powered entirely by an external RFID signal. It uses an MSP 430 microcontroller and has onboard accelerometers. The WISP communicates with the outside world by taking the data that it's collected and encoding it as a tag ID, and then sends the tag ID out to a RFID receiver. We're using two optically polarized RFID antennas, and we're using the Impinj Speedway R220 reader. Now, the software of our system is going to be running on a PC or a laptop and has four major responsibilities. It needs to collect data from the reader. It needs to determine the velocity of the remote sensor. It needs to determine the position of the sensor. And then it needs to send that data onto the graphical user interface. In order to access the data, the software will use something called the low-level reader protocol. This is a communication specification that allows external software to communicate and interact with an RFID reader. Once the software has collected the data, we'll need to parse the tag ID that's come from the WISP remote sensor to extract the accelerometer data. Once it's extracted the accelerometer data, we'll use an algorithm to calculate the velocity of the WISP based on the accelerometer data. Now that will tell us about the relative motion of the WISP, but it won't tell us about the initial position and the initial orientation. In order to determine those quantities, the software will analyze the difference in the signal strength that the two antennas have received from the WISP. That should give us information about the orientation and distance of the WISP from the antennas. So once the software has calculated those quantities, has calculated the position and the velocity, then it's the responsibility of the software to send that data on to the front-end graphical user interface. And we have a couple of options here. We can either write that data to an XML file, or we can create a socket so that the back-end software can communicate directly with the graphical user interface. So we anticipate several risks and challenges in developing the back end of this system. The first risk that we face is damage to equipment during testing. The Impinj reader and the MooWisp remote sensor are both extremely expensive pieces of equipment, and we can't afford to replace those if we damage those during testing, so we need to be very careful with those. We also foresee that developing software to calculate position and velocity will be very time-consuming. We think that the algorithms will be very challenging to come up with. We also need to become proficient in the low-level reader protocol and a language like C# or C in order to be able to effectively use the data that we're getting from the WISP. Also, determining the proper configuration of the hardware will be another challenge. We're going to need to experiment with the position and orientation of the antennas in order to find out the configuration that will give us the best data about distance and orientation for the remote sensor. And finally, we think another challenge will be integrating this system with the front end. It's critical that the back end software communicates effectively with the front end graphical user interface. And with that, I'll pass this on to Bula.
Thank you, Dan. In developing the graphical user interface, the team chose to go with a method that allows for enhanced human-to-computer interaction. And so we've decided that we want our user interface to be both interactive, it's aesthetic, as well as user-friendly. So we've decided to actually embed or incorporate a 3D module that will enhance that interaction between the human eyes and the computer as well, which Monglin will be discussing later on. In addition to that, we're aiming to use to make the actual user interface, the software altogether, cross-platform compatible as a secondary goal. And so we're going to be using technologies, applications, and softwares that are cross-platform compatible, so that if we don't reach that secondary goal, whoever comes next will be able to use the technologies that have already been implemented to be able to develop for those other platforms. Our primary platform right now is for Windows operating systems. So we're going to be using PHP and Ajax to be able to act for actual user interface by making it so that it's more of a web-based application. We're going to be empowering it using XAMPP, which is it's a freeware. It's a cross-platform compatible application that allows the user to basically set the local computer to behave as a local virtual server, which then enables the execution of PHP. In addition to that, we're going to be creating a custom browser that will enable us to activate XAMPP and run the proper languages that we need to do to be able to properly make the user interface to function. And so to create the actual browser, we're going to be using Microsoft Visual Studio for Windows operating systems. We're going to be using Xcode for Mac operating systems, and we're going to be using Qt WebKits to create the browser for Linux operating systems. So this is kind of a high-level display of how the whole graphical user interface is going to be functioning. So upon activation, the user interface is going to be communicating with the XAMPP package to get all the proper applications, proper softwares running on the computer. It's going to be querying the processor to make sure that those applications are actually there and they're active. And once it's active, the browser is going to show up. Now, on the browser, there are going to be several buttons as well as additional options. And when the user goes and wants to start gathering the information from the reader using the antennas, the user is going to be able to press a specific button. The button is going to then communicate with our back-end software, which Dan had discussed earlier, to begin querying that reader and getting all the information that we need. That back-end software is going to be either creating a data file with the proper information that we need, or it's going to be sending directly the information to the socket, which the user interface is either going to be listening to the socket, or it's going to be reading in that data file that it's creating. And so with the information withdrawn from the data file, we're going to be displaying a 3D orientation of that MU on the actual graphical user. Oh, crap. Okay, sorry. It's going to be displaying the actual 3D module of the sensor on basically this area of the user interface, and it's going to be in real life. So as you're switching, as long as the button is active, it's going to be we're attempting to make it so that it's showing a real life display of how the orientation of the 3D module is actually moving. In addition to that, we're also going to have space on the side of the graphical user interface to actually display the X, Y, and Z coordinates of that based on the initial position of the MU with relations to the antenna. It's also going to enable the user to be able to read the message inside the RFID sensor, and it's also going to be displaying it on the sidebar. The user is going to have the option to stop reading in the information as an option, as a button, and we also understand that there's time when there are several RFIDs in the area, and therefore we're going to have a drop-down that will allow the user to actually be able to choose which one they would like to view at a specific time. Some risks and challenges we are thinking that we're going to be facing. One is with the XAMPP package. XAMPP right now allocates a port which is used by many common software such as Skype and TeamViewer, which is port 80. And so we as a team are going to have to go back and see how we can reconfigure XAMPP so that it uses a less commonly used port and it's able to successfully run while the user is on XAMPP, on Skype or on other applications that use port 80. Another thing is the current method that we're currently going with in the way in which the custom browser is going to be running is that it's listening to a specific, to the processor list to see if the proper applications are being launched. Conflicts that may be is if the computer is slow, it takes more time for those applications to properly, to be fully active for the custom browser to function. It's going to make the entire launch to be slow as well. So we have to find a way to make it so that it's not as dependent on that processor list and it's more self-dependent. And the third thing is, again, our secondary goal is to make it cross-platform compatible. So finding a way to make it so that these browsers functions appropriately throughout the different browsers that we're going to be, the different platforms that we're going to be developing. I'll now pass it to Mong Lin, who will be discussing the actual 3D module we're going to be undertaking.
Thank you, Professor. Okay, hi, I'm Mong Lin. I will briefly describe our 3D design part. As we know, not everyone has engineering background. So if we want them to get easily understanding of our project, we can show them how our project works visually according to the 3D design. As Dan just said before, we have our MU sensors here and antennas here. Now we want to find the distance between our MU sensors and antennas by finding a triangular distance of it. Also, we want to find the angle of our MU sensors with each initial position according to the data from accelerometer. So what we will do in our 3D design part, we will create 3D design of our MOO, and then we set antennas as our camera, and show the dynamic orientation between our MOO and the antennas. So for our design procedure, first, we will create 3D design of our MOO using the software SketchUp, which launched by Google, and then extract our 3D design to a cloud file, a file that could be converted to the GenCS file that could be worked with the JavaScript to show our orientation between our MOO sensors and antennas. Here is what we will get finally. Like this is airplane. What we will put finally is our MOO sensors here. Now we can change. We also set our antennas as a camera. We can change it to any angles we want. Now it can change to the left, up, and down. We also could bend this to this angle or this angle. Also, we can move it far away from our camera or near to our camera to show our distance between the antennas and the MOO sensor. Actually, in final design, instead of controlling it by mouse, we can also import the data from XM file to get actual control of it. So our design day, we will create the real-time 3D design of our final application. So its MOO is just a sensor. We can implant it to anywhere we want for detection. So what we will do is that we will implant our MOO sensors into our final application. It could be a car or a robots. So we will first create a 3D module of our final application, and then we will develop the environment for it, and then import our data from XM file to get actual control of it. So why we want to do the 3D design? The reason is simple, because it's our project design may be complicated, but we can show how our project works through the 3D design, which could be easily understood by our customers. Also, we set our target audience as the people, as the high school students or the people who didn't have so much engineering background. So in this way, it will be attractive to them. Any technology has its own risks and challenges. So for our 3D design part, the first challenge is that how to use the SketchUp software to make a perfect design of our final application or our MOO sensors. And the second is that it still needs us to figure out how to import the data from XM file to get actual control of our design. Now I will pass to Samuel, who will describe the conclusion of our project.
Hello, I'm Samuel Victor, and I will be covering the costs and the conclusions to our final design. So far, we have covered the technical aspects of our project, including the software and the programming. Whereas these portions of our project have come at no cost, the hardware we require greatly exceeded our budget. As you can see, the Impinj reader alone was priced at over twice our budget of $500. Even so, thanks to our sponsor, Dr. Chakrabarty, we've been able to obtain all the equipment that we need. Our budget of $500 has been applied to ordering a new Impinj reader, along with purchasing one antenna and a power supply for the reader. Dr. Chakrabarty has covered the rest of the costs for the order and has also supplied us with the second antenna and 2 UMass MOO WISPs, along with the header board and the programmer required to program the MOOs. To conclude our final design, this diagram illustrates the functions of our designs and how they will come together. The back-end program will begin by initializing the reader and importing the MOO's ID tags that have the sensor data encoded onto them. The reader program will then add the read time and the signal strength to each ID tag, and then next the program will parse the sensor data from each tag ID. In this case, we will be extracting the accelerometer data from the MOO. Finally, we will use that data to calculate the position and orientation coordinates of our MOO with respect to the antennas. It'll export that data to an XML file or an open port that will be interpreted by the front-end user interface. The data in the XML file or in the port will then be read in by the front-end user interface, displayed to our user, and presented in our 3D model. To review some of the risks and challenges of our final design, our hardware is going to have to be set up so that we can consistently compute the position, orientation, and motion of the MOO with respect to the antennas. In order to do this, we will have to find an optimal position to place the antennas in with respect to the MOO. Also, we will be using multiple software platforms that we are going to have to integrate together in order to achieve a user-friendly front-end application that will also be able to display a real-time 3D model of our MOO sensor. Some of the software that our team is going to be using is software and programs that we are not familiar with yet, so it will take us time to learn all of these and be able to create a data display that is accurate enough for our user to use and easy enough for them to just click with one button and obtain all the sensor data that they require. And as a presentation recap, we have taken you through our team introduction, introducing you to our team GUI-MOO. We have gone through the background of our project of how these MOO sensors will be used to read sensor data from infrastructural buildings around the United States and the nation, and be able to make that data be transported into a GUI interface that would be easy for our user to read and solve their solutions. We went through the back end of our program, which is the part of our project that communicates from the software and the reader and calculates the data that we need, the position and the orientation of the MOO WISP, and then the front end that interprets that data and displays it to the user in a perceivable, usable manner. And then we also went through our 3D design that we will use to display to any user the orientation of our MOO WISP. And then I just went over the conclusions of our team management, the cost, and some of the final designs of our project. Thank you.
Any questions? Yeah.
Already being twice over your budget, do you guys have a backup plan if something fails or breaks?
Well, twice over our budget is a little bit of an exaggeration, where actually we spent our budget, we're out of budget, that's for sure, but our sponsor covered the rest, so we're not twice over budget technically. As for if anything breaks, can we replace it? The MOO is the most dangerous piece because those are handmade. They take a long time to arrive and everything. So what we have is we have RFID tags that they don't have an accelerometer or anything, but they do allow us to read the same type of data line that the MOO would give us. So we're going to use those to do a lot of our testing, and we're going to try and limit the use of the MOO. Other than that, everything's pretty heavy duty. I mentioned earlier that they're actually thinking about installing this stuff eventually on a semi-truck driving down the highway. So as long as we're somewhat careful, we should be all right with the reader and the antennas. But the MOO, yeah, we do have to be careful with those.
Okay.
Other questions?
So why do you need the web browser? Like,
The reason we chose to use the web browser, as I said earlier on, in going about to figure out what programming language to go and use to either communicate with the socket or import the file, the one that we were thinking of were mostly C#. C# is fine if we're only trying to go at it to develop in Windows operating systems, but it's not completely fine if we're trying to go with Mac OS and whatsoever. It adds complexity to it. And so we found a package, XAMPP, which allows for PHP and is cross-platform compatible. And so the reason why we're moving towards the custom web browser is because we can use Visual Basic to activate files that are in the same location as that custom web browser.
okay.
And so we're going to be using that custom web browser to actually be able to activate XAMPP, and then when the browser actually opens, all the executions, all the languages that we need are already set up for us to be able to execute PHP. It's the same thing again. Xcode enables us to be able to do that as well. with Mac operating systems, and so does Qt WebKits as well.
Qt itself is cross-platform inherent.
It is. The reason why we're planning to go at it later on is because we're more familiarized with Microsoft Visual Studio, and our first goal is to get it to function for Windows. So Qt would be something that we'd look into as a secondary thing, and then if we like it, we might just go ahead and get rid of the ones that we've made and just go with Qt's.
Qt writes just like C++.
Oh,
I used it for 3 months, 2 summers ago. It
Oh,
writes
okay.
just like C++. You'll find it really easy to pick up. It has its own GUI maker, and you can plug it into Visual Studio if you want to use Visual Studio's tools for like debugging.
okay. So we might just end up shifting to Qt and make all of our developments through there.
Yeah. And then you wouldn't have to worry about open internet ports using Xampp.
Yeah. Okay, I see.
Because if it's over the internet, you need port 80.
Yeah.
That's HTML. Everything uses port 80.
Yeah.
So, just some ideas.
Yeah, that's-
Any other questions? All right, thank you very much.